In this session we will actually do an alternative to the observable energy. Now we've been talking about the generalization of the Eigen equation to a general Hermitian operator, say A hat. So now the time has come to actually make those A hats concrete. We've done it for energy, so in this session we will do it for momentum. So we will find a momentum operator with momentum eigenstates and momentum eigenvalues, and we will start, because I've run out of board as usual, we will start on the position operator, so x hat if you like, and the momentum operator p hat. Okay, so next chapter we will do the same thing for angular momentum operators and eigenvalues and eigenfunctions, and similarly for spin. Okay, so as we get into this more and more, you'll appreciate the importance of this whole Eigen equation idea. Right? So when the time has now come to, as the Americans say, to bite the bullet. You have to actually act. The time has come to actually do it. So how do you go about doing that? Finding the corresponding operator, finding the operator for energy, the energy operator, the Hamiltonian operator, that sort of fell out fairly easily from thinking about the Schrödinger equation. So how do you do it in general? If you want to generalize this idea of the Eigen equation to other observables, well, what approach to use? How do you do that? Well, one guiding principle is Bohr's. It's called the Correspondence Principle, and just from the label you can probably guess. So what exactly are you corresponding? What two things correspond to each other? Well, in essence, classical mechanics and quantum mechanics. So the basic idea, the intuitive idea of Bohr's with the correspondence principle is that in the limit as quantum mechanics merges into the behavior of classical mechanics, then that merge needs to be sort of smooth. So in other words, you need to set up your quantum mechanical descriptions, your math and your models and everything, so that that transition as you head towards classical mechanics, that transition is smooth, right? So that there is a kind of correspondence between the quantum mechanics and the classical mechanics. Like you do not want to have something in quantum mechanics that's wildly different and incompatible, incommensurable with classical mechanics. You want quantum mechanics so that is set up in such a way and described in such a way that it merges into classical mechanics in the appropriate limits. For example, when quantum numbers become large, for example in the simple harmonic oscillator, when the energy levels get very, very high, when your E of n, when your n is very large, then things should start behaving the way they do in classical mechanics. That kind of thing. So you can use this principle to help you in guessing or suggesting potential Hermitian operators for a given observable. So now, with that in mind, let's now we can do it for energy, and by using the energy observable, we get a strong clue about what the corresponding momentum operator should be, and it works as follows. Now, in classical mechanics, the energy, the total energy of some simple system is usually its kinetic energy, p squared, in other words the momentum squared over 2m, that's the kinetic energy, plus the potential energy, right? The total energy of your system for example, a charged particle or whatever. Okay, so kinetic energy plus potential energy. Now, here is our energy operator, commonly called the Hamiltonian operator, or just the Hamiltonian, is here. Okay, this is in the one-dimensional form. So d squared dx squared plus v. Now, by the correspondence principle, you want this to sort of match with that in a sense. Now the v's obviously match, so let's suggest this gives us a clue that the correspondence between classical p squared over 2m and the energy operator would be h bar squared, and the two m's here, d squared dx squared. Or so that's p squared. So your energy operator, your Hamiltonian, in 3 dimensions takes this form. So you've got a del squared here instead of just d squared dx squared. Del squared from vector mechanics. You know, keep referring to it. So if you have not studied vector mechanics, either do so yourself or wait a couple of months, I guess, for me to get round, because I have many courses to do, to get round to undergrad level vector mechanics. I will give a course on that, because these sort of things keep cropping up. Alright, well look, have a look at this p squared over 2m, and have a look at this term here. So there ought to be some kind of link or correspondence between this term and this term. Okay, the v's are the same, so that's no problem. So here's his suggestion: let your momentum operator, right, that you will use in a momentum observable Eigen equation. Right? So here's the suggestion. So let your momentum operator, so p hat, okay, be 3 bars here, so it's defined as minus h bar dbdx, or in 3-dimensional version, minus I h bar del. The del from vector mechanics. Alright. You may ask, well, why the minus? I'll explain that a bit later. But anyway, here's a tentative suggestion. Because if you have p squared, you'll get h bar squared and d squared dx squared, or from 3d del squared, which is what you've got here. Okay, so from the correspondence principle, looking at the energy terms in classical mechanics and the equivalent in quantum mechanics, the clue is that maybe the momentum operator should be of this form, because if you apply it twice, you'll get h bar squared dbdx times dbdx, so d2x squared dx squared, or if you're doing 3D version, you get del squared. So this looks very plausible as a potential momentum operator. Okay, so let's run with it. Let's try it. We'll take it, accept it, and see what we can do. So therefore, here's your Eigen equation for momentum, for the observable that is momentum, right? So here's your operator. Let up be your eigenfunctions. Now we'll be solving for these, right? It's an Eigen equation. You're trying to solve this equation. So you're trying to find what these eigenfunctions are, and so we rewrite p hat as minus I h bar del. Here it is here, right? So that's your operator. So this is just a rewrite, but it's an Eigen equation. So on the right here, you want the eigenvalues, and you want them to be the allowed momentum, momentum, right? A whole set of them. Okay. So operator eigenfunction, eigenvalue, eigenfunction. So here and here, or actually here, right? Because this now is our momentum operator. Okay. So this is your Eigen equation, right? With these as your these p's here as your eigenvalue. Well, solving that equation is pretty trivial, right? It's just this. Now there's a bit of a complication about the normalization factor here. Now we talked about that several lectures back, lecture 4 in fact. You remember so that the normal, when you take the Born approximation, you square this and integrate it over all space. In this case, all momenta. You don't want it to blow up. You don't want it to go to infinities. So you do those tricks. You have that cycle. Well, you can do something similar. You can confine the whole system to a box of length L or whatever, or a cube of length L. So we talked about this before. It's a kind of trick to solve the normalization problem that we talked about in lecture 4. And the solution was you put the system in a cube or that kind of thing. So of length L. So this became your normalization factor. And the solution to this equation is just an exponential form. I vector p dot r vector divided by h bar. Right? Now p you can rewrite as h bar k. That's the de Broglie formula. K just being the wave number, 2 pi over lambda, and lambda is the de Broglie wavelength. It's the wavelength of your wavicle, right? So you can rewrite the p as so you got p here over h bar, but p is h bar k, so you just left with k here. So here are your solutions to the eigenfunctions. Right? They're just they're plane waves in effect. Right? So they're just plane waves where you're of wave number k, right? Heading off in direction r. So we've got a solution now to our the eigenfunctions. They're just plane waves heading, like if that's r, they're heading that way where that's your r vector going that way, and of wavelength or wave number k. Right? So now I can go back to why the minus here. Well, if you had plus, you'd end up. You can do that for homework if you like. If you had plus, you'd